Okay, let us move on to the next problem. Example number 2. A simply supported beam of span L and constant EI supports a concentrated load P at the center of the span. Estimate the maximum deflection in the beam. So here they have not asked bending moment, but however you need the value of bending moment directly to find out the deflection. In case of point loads, we cannot use actually the finite difference method to find out the bending moments. However, we know because it's a simple load, directly you can get the bending moment diagram, because for a simply supported beam with the center point load, the maximum bending moment is PL by 4, right? And let us represent that as M by A diagram. PL by 4 EI will be the M by diagram, and because it's a finite difference method, so we'll have to divide the given beam into number of parts, number of divisions. So let us divide it into 6 parts. So if you divide it, you need to calculate the ordinates at point number 2, 3 and 3, 1 and 2, 3, 4, 5, 6. Since at the center point, the maximum bending moment is PL by 4 EI, and by using similar triangles, you can get the bending moment at point number 2 and point number 1, and they are equal on the other side. So P2 is equal to P4, P1 is equal to, moment at point for M4 is equal to M2, M1 is equal to M5. So by similar triangles you can get this, and by symmetry you can get the other bending moments, other two bending moments. This you can directly get it, okay, by knowing the formula and applying similar triangles. Okay, so the deflection can be obtained by applying finite difference method. Now apply the finite difference equation, that's nothing but central difference method for point number 1, 2, 3, 4, 5 respectively. So we know the equation given by yn minus 1 minus 2 yn plus 1 is equal to h square into mn by ein. Okay, ei. So at point number 1, n is equal to 1. So therefore at point number 1, n becomes 1, and which is equal to 1 minus 1, 0. And then this is 1, 2 y1, and yn plus 1 means, because 1 plus 1, 2, therefore y2 is equal to, substitute the value of mn at point number 1. What is mn? PL by 12 EI. So just substitute that, PL by 12, and into what is h is equal to? H is equal to L by 6, that is the whole square, and keep that as it is, equation number 1. Similarly, next at point number 2, n is equal to 2, 2 minus 1, 1, and n is equal to 2, so 2, so 2 minus y2, sorry, 2 into y2. Next 2 plus 1, 3, therefore y3, which is equal to h square is L by 6 the whole square. Okay, and mn value is nothing but PL by 6 EI. PL by, substitute the value PL by 6 here, so by EI, and that is equation number 2. Call it as equation number 2. Next, point number 3. At point number 3, here point number 3, y2, 3 minus 1, 2, and this is 3, y3, and 3 plus 1, 4 plus y4, which is equal to h is nothing but L by 6, because 6 parts, 6 L by 6 the whole square, and the maximum mn moment at this point number 3, m3 is equal to PL by 4 EA. Substitute that. Okay, and then at point number 4, that becomes the same thing. Okay, because y3 is equal to y5. You can substitute the value of n here, so that becomes equation 4. y3 minus 2y4 plus y5 is equal to L by 6 the whole square into PL by 6 EI. Whereas here the value of m4 is equal to m2, which is equal to PL by 6 EI. That's what it has been substituted. Next at point number 5, y4 minus 2 y5 plus y6 is equal to L by 6 the whole square, and this value is equal to PL by 12 EI. Okay, now after obtaining these equations, let us apply the boundary conditions. What are the boundary conditions? The boundary conditions are given by that is deflection at we know if you in case of simply supported beam with the point load at center, the deflection diagram looks like this, okay, and this is y0, y1, y2, and here y3, y4 and y5. You can see y0 and y6 are 0 because at supports deflection won't be there, and we know that y1 is equal to y5 and y2 is equal to y4. These are the conditions which we need to consider, okay. Those are the boundary conditions. Now applying the boundary conditions from equation, so apply the these boundary conditions to equation number 1 and 2, okay. So if you apply the boundary condition here for equation number 1, so what actually happens? So y0 is 0, okay, minus 2 y1 plus y2 here. So you can see here plus y2, which is equal to, simplify it. So L square 6 square 36 into 12 will give you 432, okay. You can see here. So 1 by 12 into 1 divided by 6 square, which is equal to 1 by 432. Therefore PL cube by 432 EI. So that is from equation number 1. And now you can further simplify. So you send this y1 the other side. So therefore y2 is equal to 2y1 plus, okay, negative becomes positive. 2 plus 2y1 plus PL cube by 432 EI. Next, similarly, what you need to do, you consider equation number, okay, from equation number 5, you can just take, equation number 5, you can just take it. Okay, I think it's not required actually. So from equation number 2, next, from equation number 2, substitute the value of y2 here, okay. So in equation number 2, substitute the value of y2, which is nothing but 2y1. You can see here what is equation number 2, y1, okay, y1 minus 2y2 plus y3 is equal to L square by 6 PL by that. So you just need to substitute this y2 equal to whatever we have got it. So now let us substitute that value y2. So y1 minus 2 times 2y1 plus PL cube by 432 EI plus y3, which is equal to, upon calculating this one, so this value will become 1 divided by 6 square into 1 divided by 6. It will become 1 by 216. That is what it has been considered here. So 1 divided by 216 as usual here. What do you have it? So only what difference is, you have substituted the value of y2 here, y2. Now we know that so with this, actually further simplification, what you do, this will become 4 y1 minus 2 into 2 4 y1 plus 2, it goes by 216 times, therefore minus PL cube by 216 EI it will remain, and now y1 minus 4y1 it will become minus 3y1 plus y3, and if PL cube by 212 it goes to the other side, it will become PL cube by 216 plus PL cube by 216. It will become, you can see here, 1 divided by 216, and one more 1 by 216 is there. If this goes to the other side, it will become plus 1 by 216. So therefore plus 1 divided by 216, which has become 1 by 108. Therefore PLK by 108 EI. And now what do? You substitute the value of y3 in terms of y1. Therefore get it in terms of y1. Okay, y3 is equal to, send this the other side, so PL cube by 108 EI plus 3ei, I mean 3y1 it will become. Okay. Next, now consider equation number 3. What is actually equation number 3? Equation number 3 is, we have here y2. So we can just yeah. So we have equation number 3 is y2 minus, equation number 3 is y2 minus 2y3 plus y4 is equal to L by 6 the whole square into PL by 4ei. Okay. Now what you do here, you substitute the value of y2, which is nothing but 2y1 plus PL cube by PL cube by 432ei, and also we have y3 value, right? Y3 value you substitute in this equation. Okay. And plus y4. What is y4? We, since y4 is equal to y2. Okay. So substitute the value of y2 again. So that's nothing but y2 value we know already, which is equal to 2y1 plus PL cube by 432ei. We know here. So y2 is equal to 2y1 plus PL cube by 432. That is what we are substituting here. Okay. In this equation. Actually this is y4, and we know that y4 is equal to y2. So this will become y2. Y4 will become y2. Or directly you could have written 2y2. So 2 into y1 plus PL cube by 432 also you could have written. No problem. Okay. Now next step it will be the same. So 2 times this will become, and the remaining minus 2 times y3 it will become. Okay. Next, as you have seen, as I told you, so we will be multiplying this equation now 2y1. So 2 times 2 into 2y1 4y1. Okay, 2 into PL cube by 432ei, it will become 432 will become 2 by 432. 2 by 432 it will cancel out. So 216 times. So 216 is 432. So therefore 216 it will become. So PL cube by 216ei minus, so 2 into 54. Okay, this will go 54 times. Okay, therefore PL cube by 54ei, and minus 6y1 it will become minus 6y1, right, which is equal to PL cube by 144 ei. How this has happened? 142 ei, that's nothing but from this equation, from the equation number 3, you can see the value. So in equation number 3, you can see L1 divided by 36, okay, L square by 6 square 36, right? So therefore 1 divided by 36 into 1 divided by 4, which is equal to 1 by 144. That is what this means. So 144 ei, therefore PL cube by 144 ei it will be, right? Now next step, you can see here minus now here minus 6 ei plus 4, I mean minus 6y1 plus 4y1, it will become minus 2y1 minus PL cube by, so if you calculate this 1 by 54, okay, 1 divided by 216 minus 1 divided by 54, it will become minus 1 divided by 72. So PL cube by 72 ei negative, because this is positive, I mean negative, the highest value is negative only, right, which is equal to PL cube by 144 ei. Or you send this the other side, what actually happens, 1 divided by 72, because this, if it goes to the other side, it will become positive. Now this is negative, if this goes to the other side, positive. Okay, therefore this will be negative plus therefore minus 2y1 is equal to 1 by 72 plus 1 by 144, which is equal to 1 by 48. PL cube by 48, or y1 will become, so because this is negative sign, minus 2 if it goes to the denominator, 48 into 2, 96. So the deflection at the point number 1 is given by minus PL cube by 96 EI, right? But we don't know whether that is right or wrong because we don't have any idea about the deflection at point number 1. Now let us move on, and we have an idea for deflection over here. What is the deflection in a simply supported beam with a point load at center? That's nothing but PL cube by 48 EI. Let us see whether we'll be getting that or not. Okay. So now next, so we know the relationship y3 is equal to we have PL cube by 108 plus 3y1. So PL cube by 188, keep it as it is, 188 EI minus 3 times y1. Okay, the value of y1 is PL cube by actually this is plus, okay, plus of y1. Y1 is negative value. Okay, so plus of minus 3 times y1, which is equal to PL cube by 96 EI. If you just do that and if you simplify it, so what actually you will get it? So you let us see, 1 divided by, you have it, so 1 divided by 108, okay, minus, right, minus 3 divided by 96, which is equal to 19 divided by, this will be equal to 19 divided by 864 PL cube by EI, okay, or once again you can check it out. So 1 by 108 minus 3 by 96. Okay, now so you just divide 864 divided by 19. So 864 divided by 19, so which is equal to 45.47 or 45.4. Therefore 1 divided by, so this goes by 45.47, which is equal to 45.47. Therefore the maximum deflection at center of the beam in case of simply supported beam, which is given by from the finite difference, which is given by PL cube by 45.5 EI, but actual deflection from exact method, which is given by deflection y is equal to PL cube by 48 EI. So there is a very little difference which is there over here, but actually since we have considered 6 parts, we could get 45.5 EI, but you can check the textbook value. So in that one the deflection is coming equal to 43 point something. So we were not that accurate. So if you wanted to get to be accurate, you need to consider more divisions. You can see here in case of point load with 4 parts, the maximum deflection value you got it equal to PL cube by 42.66. okay, actual value is 1 by 48, PL cube by 48, but it is not so, right? So hence as you consider more divisions, so you come and you will get a little accurate answer. Instead of 42 we have got 45, so which is nearest to 48. So that is what we can conclude. If you divide the given beam into more number of pieces, here you will get accurate answer. Okay, so that is that's all for this problem. Okay, that's how you need to find out the maximum deflection in case of point load. Right, next let us move on to another problem. That's nothing but a simply supported beam with UVL. Okay, let us consider a simply supported beam with UVL load, uniformly varying load. Okay, so a simply supported beam, the problem goes like this. A simply supported beam of span L supports a triangular load of intensity W at the center of the span. Okay, this is W kilonewton per meter, and 0 at both the ends as shown in the figure. Estimate the moments. Okay, we need to find out the moments as well. Okay, and maximum deflection at the center of the span. Maximum deflection at the center of the span. Okay, so those values we need to find out. Now let us yes, okay, this is the given problem, and in the problem only W will be given. So what you need to do, you need to calculate the value of W2 as well. I mean the value over here. So this is W0, W1, W2, W3 and W4. As I've already told you, Wn, W0, W1, W2, W3, W4. Now let us apply the finite difference method or finite difference equation for this problem. Okay, so we know that is the equation given by mn minus 1 minus 2mn plus mn plus 1, which is equal to minus wh square. This is the equation we know, right? Now let us move on. Then now apply this equation over here. Okay, at point number 1. Okay, because we know that at point number 0 and 4 the bending moment is 0. Only we need to find out bending moment at point number 1, 2 and 3. Okay, now so bending moment at point number 1 is given by that equation we will be getting. So you just substitute at point number 1. You just apply finite difference method at point number 1, 2, 3. That's all. We are not calculating directly the bending moment now. We are just applying the finite difference method. That means we will be formulating equation at number 1, point number 2, point number 3, and then applying the boundary conditions, simplifying them. We will be getting M1, M2, M3 values. Okay, that is what we do in finite difference method, right? Now, okay, so if you apply finite difference method at point number 1, so 1 minus 1 0, and this is point number 1, so 2m minus 2m1 plus 1 plus 1 2, which is equal to, and here this is actually Wn. What is Wn here at point number 1? W by 2. So that is what it has been substituted here. So Wn is equal to W by 2 h square. Okay, that is called that as equation number 1. This is at point number 1. Next at point number 2, okay, at point number 2, n is equal to 2 minus 1, 1, and this is n is equal to 2, so 2m2 minus 2m2 plus 2 plus 1, 3, m3, and which is equal to minus wh square. What is Wn here? Wn is equal to W, therefore it will become wh square only. Next, consider point number 3. Let us apply the method, this method at point number 3, which is equal to m2 minus 2m3 plus 3 plus 1, 4 m4, which is equal to, and again here W2 only, W by 2 only. Okay, so minus W by 2 into h square, and you call that as equation number 3. Now we have the boundary conditions are the known bending moments, which is nothing but m0 and m4 are equal to 0, m0 and m4 are equal to 0, and by symmetry m1 is equal to m2, I mean m3, m1 is equal to m3, and this is actually m by a diagram. Actually you could have written in the upward direction also, no problem. We are considering this as positive diagram, right? So m1 is equal to m3. So these are the conditions we have. Now from equation 1 and 2, okay, now let us consider let us apply the boundary conditions for equation number 1 and 2. So if you apply, we know that m1 is equal to 0, therefore 2m1 plus m2, which is equal to minus wh square by 2. Therefore if you send this 2m1 the other side, m2 is equal to minus wh square by 2 plus 2m1. Okay, so you got the value of m2 in terms of m1. Now similarly, now from equation number 2 we know m3 is equal to m1. Okay, this is m3, right? This is m3, m2, m1, m0, m4. m3 is equal to m1, so you can substitute this m3 is equal to m1 here. and we have the value of m2, we just now we got it, you substitute here, therefore m1 minus 2 m2 is this is the value of m2 minus wh square by 2 plus 2m1 you substitute here, so that you will get over here, so plus m1 substitute, which is equal to minus wh square, right? Now next, upon simplification, okay, upon simplification, 2 this m1 plus m1, 2m1 it will become, okay, 2m1 plus minus 4, 2 into 2, 4m1, and minus is there, minus into plus minus 4m1 plus this 2 into this 2 will cancel out, so plus minus into minus plus wh square, which is equal to minus wh square, and apply, then minus 4 plus 2, it will become minus 2, okay, minus 2m1, and if this goes to the other side, plus wh square will become minus wh square, so minus wh square, it will become minus 2 wh square, okay. Therefore m1 is equal to this 2 minus 2 will cancel out, therefore m1 is equal to wh square. We got the moment over here, wh square by ei, okay, m by ei value we know, that's all. Actually we don't have any idea, we have an idea over here what should be the bending moment value here, okay. Let us see now we substitute the value of m1 in this m2 equation, okay. You can call this as equation number 4 actually. So from equation number 4, okay, so from equation 4, m2 is equal to minus wh square by 2 plus m1 is wh square plus wh square, so 2 wh square minus half wh square, how much it will be? 1.5 wh square, that's all, right? So m2 is equal to 1.5 wh square by 2, and what actually so you can substitute the value of h here, h is equal to L by 4, so that will become 1.5 w into h is L by 4 the whole square, L by 16, so this will become okay, 1.5 w L square by 16, or this will be 3 w L to the power of L square divided by 32 it will become, okay, because this 1.5 if you multiply with 2 here and 2 below, so 3 into 32, so 3 WL square by 32 will be the maximum bending moment at the center, okay. And also we know that if you know the value of m1, that is equal to m3 as well. So we got all the bending moment values from finite difference method. This is how we need to do finite difference method bending moment calculation. Now let us consider the calculation of the deflections, okay. So same way we need to apply. Now what you need to do is you have to consider this m by diagram, so you have to consider this m by a diagram as the load acting on the simply supported beam, and for this loading diagram you just need to apply finite difference method. Consider this as the load and calculate the deflection, okay. So applying finite difference method, okay, in this equation what will happen at point number 1, 2, 3. So we need to consider, so let this be point number 1, 2, 3, okay. We need to apply finite difference method at point number 1, 2, 3, because anyhow deflection at 0 and 4 are 0 values only, okay. Now applying finite difference over here at point number 1, 1 minus 1, 0, 1, and 1 plus 1, 2, so therefore y0 plus 2y1, y0 plus 2y1 plus y2, which is equal to so here this will become, actually what is the equation, yn minus 1 minus 2yn, okay, plus yn plus 1, okay, is equal to the equation is mn by ei into h square. Okay, that is the equation, right? Now what you need to do, so mn, what is mn here at point number 1? At point number 1, wh square is the value, so therefore h square and wh square, so wh square by wh square into h square by ei, so that's what we will get it. So this is the, you call this as equation number 4. Next, let us apply at point number 2. So if you consider at point number 2, 2 minus 1, 1, and this is 2, so therefore 2y2 plus 2 plus 1, 3, therefore y3, which is equal to mn over here. We got actually m2 is equal to 1.5. This is nothing but m2, isn't it? So therefore 1.5 wh square, right? H square divided by ei into 1.5 wh square. That's the value of mn is m2. Okay, because n is 2 here, so n2 is equal to m2 is equal to 1.5 wh square. Substitute it here. So you call this as equation number 5. Similarly, at point number 3, so 3 minus 1, 2, and this is 2y3 plus 3 plus 1, 3 plus 1, 4 plus y4, which is equal to h square by ei into m3, and we know m1 is equal to m3, which is equal to wh square, which is what, that is what we have substituted. So these are equation number 4, 5, 6. Now applying the boundary conditions, we know that in the boundary condition we know that y0 and y4 are 0 and y1 is equal to y3. Y1 is equal to y3, right? So y1 is equal to y3. These are the conditions we know. Now let us apply these boundary conditions here. Let us consider equation number 4. So from equation number 4, y0 is equal to 0. So plus minus 2y1 plus y2 is equal to h square ei by w square. So therefore y2 is equal to, you send this minus 2y the other side, therefore minus 2y the other side, therefore y2 will be equal to 2y1 plus wh to the power of 4 by ei. Okay, this is the value of y2. And next, from equation number 5, so for this is the equation number 5, you substitute the value of y2. Okay, and also we know that y3 is equal to y1. Okay, therefore y1 plus y1, 2y1 minus 2y2 is equal to 1.5 wh to the power 4 by ei, and we know y3 is equal to y1. Yeah, that because of that only it has become 2y1. And now further simplification, minus 2y1, okay, minus 2 into y2, substitute this value, 2y1 plus wh to the power 4 ei, which is equal to 1.5 wh to the power 4 by ei, and minus 2y1, right? Yeah, here, so thing is, this will become, there is, you can see here 2y1 minus of 2 into 2, 4y1, so 4y1 plus 2y1, which becomes minus 2y1 minus of minus 2 into this much, minus 2 wh to the power 4 by ei, okay, which is equal to 1.5 wh to the power 4 by ei. So now 2 minus 2y1 minus 2 wh to the power 4 by ei, which is equal to this much. Now simplify it. Minus 2y1, you send this to other side, therefore 1.5, and this will become plus. So 1.5 plus 2, it will be 3.5 wh to the power 4 by ei. Therefore y1 is equal to minus 1.75, 3.5 by 2, 1.75 wh to the power 4 by ei, which is equal to, y1 is equal to minus 0.0068 wL to the power 4. Actually speaking, you just substitute the value of h is equal to L by 4 and then simplify it. This is the value you're going to get actually. So you substitute h is equal to L by 4. This is the value you're going to get. Next, substitute the value of y. Okay, so substitute, we know the equation y2 in terms of y1. Now substitute the value of y1 here. So you will get y2 value equal to this much. Y2 is equal to minus 3.5. Okay, this is minus 3.5 WL to the power 4 by, actually WH to the power 4 by EI plus WH to the power 4 in this equation, and thus that is simplified to, because minus 3.5 plus 1 minus 2.5 WH to the power 4 by EI. So by that you will get the value of y2 is equal to minus 2.5 WH to the power 4 by EI. That is the maximum deflection, and if you substitute H is equal to L by 4, this is the resulting value. Okay, so this is how we need to find out the deflection and bending moments using central deflection method. Okay, let me just summarize what we have done. Okay, is you will be given with a beam. Okay, so what we have done in finite difference method, I'll just summarize. Okay, you just forget about the first class where we have derived and we have got so many equations and all. Okay, just forget about them. What you need to do, what you need to remember is just one equation out of that. So delta square y is equal to yn minus 1 minus 2yn, okay, plus yn plus 1, right? This is the equation which you need to remember. That's all. Okay, if you know this equation, and we can apply this equation to many problems. We know d square m by dx square is equal to minus w. Okay, this is from the elements only we know, strength of metals only we know. So if you know this, you just apply this concept here, this concept here. So you will get actually mn minus 1 minus 2mn plus mn plus 1, okay, divided by dx. Dx is nothing but interval h square is equal to minus w, right? Therefore mn minus 1 minus 2mn plus mn plus 1 is equal to minus wh square. This is the only one equation which you need to remember. Similarly, you also need to remember, we know the formula d2y by dx square is equal to m by ei. This is the known value. So the same thing you can apply here. That will become, from this we get an equation which is similar to this, which is nothing but yn minus 1 minus 2yn plus yn plus 1 is equal to mr. Okay, you just you consider mn into h square by ei. You will get this one. Okay, or mn by ei into h square. You will get the equation. So only you need to remember these two equations out of the first class. Okay, first and the second half of the class. Just need to remember these things. Okay. So you may not be asked to explain those methods. Sometimes if they have been, even if they have been asked also, you can just explain whatever you know. Okay, but majority you will be given with the problems. Okay, you just need to remember these two formulas. Okay, and this equation, this formula, and this is wn. Okay, and this is mn. You remember these two equations. And what you need to do in problems is, you will be given with the problem. Okay, you will be given with some beam with some load. Okay, and what you need to do, you divide the given beam into number of pieces. Okay, and they will be w1, w0, w2, w3, w4 and w5. Actually even number you can divide, let it be up to 6. Okay, and assume the bending moment diagram. So this may be the bending moment diagram, and let those bending moment values be m1, m2, m3, m4 and m5. Okay, and here m0, right? So you don't know the values, but you can find out these values by applying finite difference method. So how to apply the finite difference method? Just very simple. You know this equation. Okay, apply this equation at point number 1, 2, 3, 4 and 5. 0, 1, 2, 3, 4. Okay, you just apply this equation at all the points. You substitute n is equal to 1 here, n is equal to 2 here, n is equal to 3 here, n is equal to 4 here, and definitely m0 and m5 will be 0. Just substitute these n values in the equation. So get 4 equations. You will get 4 equations, right? And so by those 4 equations, you cannot solve the all those 4 unknowns. You cannot find out, right? But what you need to do, actually there will be how many unknowns? There will be 4 unknowns, okay? And it is very difficult. Actually speaking, there may be some symmetrical diagrams, etc., etc. So there will be some boundary condition like m0 is equal to m5, right? We'll have those unknowns, and those are equal to 0. And here you may have some symmetry in case of UDL and all. m1 may be equal to m3, and that kind of boundary conditions will be there, okay? Considering those boundary conditions, applying them here, okay, go on simplifying. Finally, you will going to get m1, m2, and m3 and m4. Okay, so by applying the finite difference method at all the 3 points, you will get some simultaneous equations. Okay, and applying boundary conditions and solving those boundary conditions will give you the bending moment values which you're going to get here. Okay, so similarly, what you need to do in case of for finding the deflections, okay, you need to assume the deflection values as, okay, y1, I mean y1, y2, y3, y4, etc., right? And apply, and where n is equal to 1, n is equal